Welcome, ladies and gentlemen, to our lesson 2 of our unit 2 involving limits. Today we're going to be studying the limits involving infinity, either the limit going to infinity or the limit as x approaches infinity. Two different types here today. So we're going to start off with what we kind of slightly defined in pre-calculus as our study of asymptotes. Asymptotes are actually based off of limits, or we can define them as limits. And the first one here is our horizontal asymptote. It's basically describing as x approaches infinity. So we're talking about our left and right end behavior. As x goes to infinity in the positive direction, goes towards positive infinity, it approaches a value b, so it would be something along this line. If I had a b right here, there would be a horizontal asymptote right here, basically saying as x gets really big to the right-hand side, my function approaches that b value. It gets really close, but will never actually be the b value. Or likewise, going to negative infinity, we would get something like this, saying it's going towards that value of b. So this is our limit definition for horizontal asymptotes. And likewise, we have a limit definition for vertical asymptotes in the same sense. If we had some a value right here and we had some sort of vertical asymptote, if we approach a from the right-hand side, the limit itself is approaching, or the function itself is approaching positive or negative infinity. So it's coming in from the right-hand side, it could go up this way, or it could go down below. It can't go both, obviously. Or likewise, if we approach from the left-hand side, we would be approaching either positive or negative infinity. I'm just going to draw it in going to negative infinity. All right, so what I have drawn here is my horizontal asymptote, or my vertical asymptote, is as x approaches a from the right-hand side, my function approaches infinity, so we would say equals infinity. Or if we approach from the left-hand side, it's approaching negative infinity. And we know if that is the case, we could ask this question right here: what's the limit? What's the limit as x approaches a of f of x? In this particular case, we would say dn e does not exist. It does not approach a single value. All right. Now, since we're technically dealing with infinities, mathematically speaking, we have to revise or restate our properties. But I discussed those properties with us last time, and it's all of our limit properties, and they're basically the same properties as lesson 1, where we had if it was the limit of a sum, it's the sum of the two different limits and that sort of thing. Really, the only thing new now is we can't plug infinity into an equation because that doesn't make sense. All right, so we're not going to be plugging in things. We're going to be looking at really stuff we know about horizontal asymptotes, and we're going to be looking at some tables and graphs and a couple little other things here. So first couple examples here. If we would like to find the limit of f of x as x approaches infinity for the function sine x over x. Well, here's the problem. There are two ways that we could think about this problem. The one way is we could think of this graphically. Well, in this graph, we know what the limit is as x approaches 0 for this function. We know it was 1. And if any of you graphed this, you would have known that this function does this, and then this, and then this, and it just keeps getting smaller and smaller and smaller as it goes to the right, and it does the same thing as we go to the left. And it's symmetric. It'll go do the same thing on both sides. But we're wanting to know what happens as x gets really big. Well, you'll notice in this graph, the y values are oscillating, but they're oscillating and getting closer and closer to a height of 0. And we would actually say that this limit is equal to 0 because the y values are getting really, really close to 0. The other way that I like to think about this is instead of writing it as sine x over x, I like to write it as 1 over x times sine of x. I know that whatever I plug into sine of x, it's either going to go to a positive 1 for a maximum or a negative 1 for a minimum. So the sine of x really doesn't have an effect as x gets really, really big. However, this does. And we know that if we take a number, 1, and we divide it by a really, really, really big number, it's a really, really small number. So as this x value gets really, really big, this fraction right here gets really, really close to 0. So we could say that this piece would be 0, and this is some number from negative 1 to 1, and it'd just be 0 times any of those numbers, and therefore our limit would be 0. So we can think about it analytically, we can think about it graphically, we could plug values into our graph and use a table, and we would see that eventually that height gets really, really close to 0. So, long story short here, in this particular case, my limit as x approaches infinity, and negative infinity in this case, is 0. All right, this one here, a little bit different style. Got a lot of extra stuff in here. But what we want to do is we want to use some of those properties to make this a simpler problem. I can rewrite this, and maybe you see this as well. I can rewrite this into something simpler, or maybe more complex, however you want to look at it, as a 5x over x plus sine x over x. And my limit property says I can find the limit of each of these separately. So I'm going to say, okay, it's the limit as x approaches infinity of 5x over x plus the limit as x approaches infinity of sine x over x. Well, here on the left one, you'll notice that I can cancel those x's, so that means I can say it's the limit as x approaches infinity of 5 plus something we just evaluated as being 0. We know that this is 0. Well, in this particular case, as x approaches infinity, my function is always 5, and therefore this is 5 plus 0, which is 5. I don't know why I circled it right now. This is equal to 5. And we're done. So the limit here would be 5 as x approaches infinity. And you notice we didn't really have to even think about infinity at all because this particular problem just simplified down to what we wanted it to simplify to. But we do have another, so erase pin here. There we go. We have another problem here. If we want to go to negative 3 as we approach from the right-hand side of this particular function. So now we're not approaching infinity, but my guess is the answer is going to be one of the two infinities. And in these particular problems, they usually say, hey, why don't you graph or use a table? Now, I hope we know something is occurring at negative 3. And we should probably know that there's a vertical asymptote. The problem is we might not know if it goes to the positive infinity or the negative infinity on the right-hand side, which is what we were looking at. So if we plugged in numbers, if we thought about a table, because you can plug this into your y1, you can go y1 equals x over x plus 3. You can go into your table, and you can set your table start. I believe I don't have my calculator here with me. Table start at, let's go negative 2.5. You got to remember that negative 2.5 is on the right-hand side of negative 3, because that's what we want to do. You can start it wherever you want, really. And if we said delta table, I would say a delta table of, we could start with 0.1, 0.1. And you could notice that as x is getting closer and closer to 3 on the right-hand side, Well, that's negative 2.5. Makes that negative, makes that positive. That would be a negative number. And negative 2.9, that's negative, that's positive, makes a negative number. And eventually you would notice it would do something like this. And I actually think it has a horizontal asymptote right here. And that's what you would get. So going to negative infinity. All right. So we can do this graphically pretty simply. You can do a table pretty simply. You need to know how to do both of these things. You need to know how to graph it and observe the graph, what's happening as we approach from the right-hand side. And you need to know how to do a table because there are some problems in the calculus that we need to do tables on. So if you don't know, you need to come see me, ask me questions. All right, let's go ahead and go forward. That was not supposed to pop up there yet. Don't write that yet. We got something else coming up first. One of the things that we're going to ask in this case is something called an end behavior model. Like what is happening to the function on the right-hand side or on the left-hand side as x goes to infinity or negative infinity. And what we're basically asking is what happens to my function as x itself gets really, really big. And I say absolute value because we're talking about big negative infinity or big positive infinity. So we want to think about what really is going to take over on our function. And we look at something simple right here. If we look at 3x, this big quartic function, eventually, as x goes towards infinity or negative infinity in this case, these things here are growing really, really fast, right? Because as x gets big, this cubic gets big, but the x to the fourth power is going to get bigger faster. 3 to the third power is 27, but 3 to the fourth power is 81. Just at 3, it's already really, really big. 5 to the third power is 125. 5 to the fourth is 625. We're now well past what the cubic is going to do. So we would say in this particular case that the right end behavior model, meaning as x goes to positive infinity, would be x to the fourth, as would, in this case, the left end behavior model. And we should understand that a quartic function is going to do something like this. As we go to the right-hand side, it's going to go to infinity. And as we go to the left, it's going to go to infinity. And that's what I mean by end behavior model. Who cares? We don't care what is going on in the middle. This quartic could be doing something like this, for all we know. But we just want to know what's the end behavior. And we dealt with this in Algebra 2 and a little bit in pre-calculus. Now, something that we're going to kind of stretch for a little bit is end behavior models for fractions or rational functions or quasi-rational functions here. And we're going to look at this definition saying that the right end behavior model for, or actually the function g is a right end behavior model if the limit as x approaches infinity of that ratio is 1, and likewise it's a left end behavior model if the limit as x approaches negative infinity is 1. So we're going to look at that here. Sorry, I don't know why I didn't put my motions on here. The first question here is a little bit different than the second question, but on the first question, this one's not really going to use, oops, come on here, there we go. This one's not going to really use that right end behavior model, left end behavior model theorem definition thing I just wrote. However, this is going to look like this. We've done this problem before. If we have f of x over g of x, we have 3x to the fourth plus 2x cubed minus 2x squared minus 8x plus 5 all over 5x to the fourth minus 2x cubed minus 3. Now, the reason I say we've done this problem before is because this is a basic polynomial over a polynomial, which is a rational function, and we know from Algebra 2 that the right and left end behavior models for this type of function are based off of horizontal, let's see if I can spell today, horizontal asymptotes. So if you remember how to find the horizontal asymptote of a basic rational function, you should be good. And in this case, since my exponents, or my degrees, are equal, notice that they're both 4, the end behavior model is going to be the function y equals 3 over 5. And that's very, very simple. Our horizontal asymptote is 3/5. If you have to remember this, that if the denominator has a bigger degree, then it's 0. And if the numerator has a bigger degree, then it's going to be the infinities, positive or negative, depending on the sign of the function. However, let's look at that definition that was on the last page for this type of function. We want to show that g of x equals x is a right end behavior model. All right, so let's see if we can do that. Come on here, erase pen. In order to be a right end behavior model, we need to look at the limit as x approaches infinity of f of x over g of x. And we're going to do like we did before. We're going to say the limit. Now remember, we're showing that it's true, and we need to use our properties to show that it's true. It's basically a proof without a lot of words. I'm going to split this up into x over x plus the limit as x approaches infinity of e to the negative x over x. All right. We already know that x over x is 1, and therefore the limit as x approaches infinity of 1 is 1. And now we need to figure out this limit. You guys notice that I'm writing limit at every single line, and you need to start doing that because most of you guys are writing incorrect statements. If I left this limit off of here, this would read that 1 plus this fraction is the same as this limit, and that's not true. We need to start writing true statements. Okay, so now we need to figure out, what does this limit do as x gets really, really big? Now, you might remember what e to the x looks like, because all exponential growth models look like that. That's e to the x. However, e to the negative x looks like this. It's just flipped across the x or the y-axis, which means as x gets really, really big, that y value gets really, really small, and it goes towards 0, while this goes towards technically infinity. But if we do 0 divided by anything, we get 0. And in this case, the limit is 1. And using that definition theorem from the last page, it says if your limit is 1, then it's true, which means, okay, check mark. We've shown that x is a right end behavior model. So likewise, we are going to show that e to the negative x is a left end behavior model. So we need to know what is the limit as x approaches negative infinity, this case, of x plus e to the negative x over e to the negative x. We're going to split this up the same way we did in the last problem. Hopefully I gave myself enough room here, which I don't think I did. But I think I can write over top of this. Oh man, can't see it. So that's saying e to the negative x over e to the negative x. All right, so first limit, we don't really know what it is yet. We'll figure that out in a minute. And we see that we have e to the negative x over e to the negative x. That's just 1, and that limit is 1. So we really hope that this limit is 0. Now, don't just say it is because that's what you want it to be. Let's verify it analytically. Let's think about what's happening. So x is getting really, really small, or very, very negative. As x gets very, very negative, this numerator gets very, very negative. Oh, well, who cares really, right? So let's think about those two graphs. This is the function x, and this is the function e to the negative x, like I had up there just a second ago. We're basically asking what happens as x goes to negative infinity. Okay, in this case, it goes to negative infinity. Well, that's kind of weird. But in this case, it goes to positive infinity. Well, now what? Well, that doesn't make sense. But if we think about this, x is just going to be some sort of negative number. And it goes at a very constant, steady rate. Now, because this right here, or this e to the negative x, gets bigger faster than x, because you'll notice that this line right here gets very, very steep very, very quickly. That's how exponentials work. That means the denominator takes over, and we're going to have some sort of number over a very, very, very large number, and therefore dividing by a very large number will equal 0, and we get plus 1 is equal to 1, and therefore we have verified that e to the negative x is a left-in behavior model. That actually finishes me up here. You'll notice I have a little note down here on the bottom. I noticed a typo. I accidentally had written 49 and 49 on your assignment sheet. That should read 49 and 53. I think I made the correction in the Google Drive. I will upload all this stuff to Google Drive in case you don't want to use YouTube, or you've probably already used YouTube to watch this. I'm going to leave you with this for you math nerds out there that would like to complete this Sudoku. Go for it. Or this Sudoku, as she says. I will see you guys tomorrow. Have fun. Have a good evening.